three-phase circuits. So what we're going to look at, quite briefly actually, is look at single phase, two-phase, three-phase, and I'm going to kind of show you why we go for a three-phase system in doing that. And then we're going to look at the relationship between line and phase voltages and currents for balanced star and delta connected systems. Look at power in a balanced star and delta system and solve three-phase system problems. Yeah. And do it with balanced systems initially, and then over the next week or two we'll be starting to look at systems when they're unbalanced and look at the conditions when you get a short circuit or someone connect the wrong size load to one of the phases, what that does to the system. Yeah? So faulted systems essentially. Single phase system. Alright? If we have the whole generation is round moving a magnet inside a coil in a circle and creating a sine wave. Flow to the the generated EMF from doing that all faster hertz, so we need you're up at side the next side current so this sinusoidal voltage, okay, sinus in the conductor. So now if we some length so if we know those instantaneous currents, with that is presents a pulsating load to the prime mover that is rotating it. So the gas turbine, the steam turbine, if you only have a single phase generator, this is not the only, But as one valid reason why you go single phase. For the usually the account certainly not suitable for get a step further with our we would get two sides, not three. Yeah. Well, it's the right. Electricians are using the on the screen. What is it? Grey with is the blue is the new black and black is the new blue. We end up with two together over that same period, you get a straight line with two phases. They average to a straight line. So the remember all power produced in that time. So a single phase, we only had one. Yep. Produced in the size of the generator. Added another core. Out of shifted to the other one. And we're going to put smooth load to our prime mover. Less vibration, less noise. Let's go one step further. Equals 20 degrees. This is the now have so 120 degrees up, which gives us 3 power pulses, right? And we get an average that is a straight. That's 3. For instance, instead of 200 from the 2 phase. You get from a single phase little or no increase in the size of the generator. Yep. You could say, why don't they go on and do 4? I haven't investigated it, but I would imagine you would then need increasing the anthem. Because there's only a little bit extra on the top. So as you add just one more coil, you're not half the, probably only get a quarter as much again for a wind and another turn. And 3 phases works out quite well for other reasons as well. Okay, because that's the issue of motors would then need for windings, and that goes on and on and on and on. The biggest thing is to make it physically big to get the. So we go 3 phase. Yeah. So balanced 3 phase power system. For the American reason, place you don't find generators connected in Delta. The reason we don't do any calculation complex and we don't need to is that's mighty as long as you're looking at that. If you unbalance the way, put 10 and 15 on the other, you'll get a circulating beating them up. Generator is always connected in star with one end. In a star connected system, meaning you need less insulation. Alright? As well, electricity, the generator voltage is somewhere around about 25 kilovolts. And then for the super grid, that's stepped up 400 kV. Yeah. So we've got 3 phases, and then there's a neutral that's taken off the star point. Right? So what we end up with is 3 lots of line voltage. Yeah. If we think about 2 of these phases, yeah. So these 2 phases connected to a load. So isolate those 2 phases there. Yeah. EA neutral and the line, yeah, and EB there, yeah. We've got the volt E line. Yeah. So by careful this EL is EA plus EB. Do you all agree with that? Minus. Yeah. We got to work. That's just a quick reminder on Kirchhoff's voltage law. Yeah. If I always draw a little bit, draw I think I've got to get this right. Put that one that way. So plus that. That arrow. You do it step by step. I always teach Kirchhoff's voltage law, right? All arrows EA. It's the only clockwise arrow. I only ever put an arrow on the end of my voltages because that shows the direction. B E line. Yeah, that's where it come from. Now if I take I is equal to EA minus EB. Don't see it.
No, I just didn't see it. How do you mean it goes round?
Shot. Nope. Thing. So the line voltage in stock times the over 2 hours. With a system, same phase voltage. Your neutral, you would relationship between phase and the three currents and IC are equal in magnitude, equal to the line current L. So current right. And that is minus two ohms resistance, 3 ohms inductance. That's a perfect react. Then they'll still cancel each other out. If in any way, you'll get a neutral. Alright? Yeah? Move on. Alright? It can be shown that for a balanced load, the instantaneous current in the neutral, by Kirchhoff's law, the sum of the phase currents is equal to, if we let the peak line current be 1, phase A is the reference phase, of flow. IB, an amp, 100 degree. these 0.66 66 plus active or